So we are Western Sydney Solar Team, and our mission is to develop new innovations as well as leaders of the future to take a stand in the inevitable shift towards sustainable solutions. And our project is a multidisciplinary student-led venture, which encompasses all aspects, including design, manufacturing, and racing solar-powered vehicles. And we have a rich 10-year history and have placed top in class during the Bridgestone World Solar Challenge in 2017, first in the American Solar Challenge in 2018, and we broke the record in 2019 for the lightest solar-powered vehicle to ever race, weighing only 116.8 kilos. And today, I want to embark on a deep dive into composite manufacturing with you. So we'll start with the basics. What are composites? So composite materials are made from two or more different materials, and when their properties are combined, they are stronger than the individual materials by themselves. The most common form of composites are fiber reinforced polymer composites, or FRP for short. They are made from a polymer matrix such as epoxy, which is then reinforced with an engineered fiber such as glass, carbon, and Kevlar. The polymer matrix allows the fibers to be protected from environmental damage, and its other critical purpose is to transfer the load between fibers. This allows the fibers to provide strength and stiffness to reinforce the polymer matrix, reducing the likeliness of cracks and fractures. By using these materials throughout our vehicle, we can engineer the car to have great tensile, shear, and compressive properties. As well as increasing the strength of our vehicles by using composites, we are capable of reducing the overall weight of the vehicle compared to alternative structural methods and materials. So in an attempt to make this first section comprehensive, I'll refer to Unlimited 3 and that vehicle's aerobody. It's just the external aerodynamic surface or shell of the vehicle, really. So the first step to manufacturing TED 3's body was to use our computer-generated design file and send it to a manufacturer to be CNC machined out of MDF. And after this process was completed, we were left with a one-to-one replica of the car. And this is referred to as the tool or the buck. So from here, the MDF was coated with vinyl ester resin to seal it from being exposed to the environmental changes in air, which could cause warping or swelling. Then the buck was coated with gel coat, a very similar paint to what's used in marine applications. The reason we chose to machine the plug out of MDF is because it's a cheap material to source and it machines really well. So in 2019, this machining process was sourced externally to the university, as we didn't have the resources to be able to machine such a large-scale buck on campus. But thankfully, due to major upgrades to our advanced manufacturing precinct, we'll be able to perform this task on campus in future using our new Bellotti 5-axis CNC. When outsourced, we use a 3-axis CNC, which limits us in regards to how advanced the contours can be in our models, as the machines can only move in the X, Y, and Z axes. Due to this, the cost of machining is quite high, as you can only machine half of the car on one side, and then the CNC would have to be stopped and reloaded to machine the other side. Our new Bellotti 5-axis CNC can cut along the X, Y, Z, A, and B axes, providing us with the capability to create the majority of the car tooling in one go. No problems with contours that have a 90-degree overhang. So when we finish sealing the buck, we spray it with 2 to 3 thick coats of tooling gel coat with added dye, generally red or some sort of bright color. Once tacky to the touch, we can start laying the fiberglass onto the buck. And it's imperative that we have pre-cut sections of fiberglass to apply. As we layer the buck with these pre-cut sections of fiberglass, we slowly apply epoxy resin and use specialized tools to knead the epoxy through the fibers. We only have a limited time to get this done before the epoxy starts to cure. You may see something laminated on the inside of the mold on the picture on the right-hand side that looks suspiciously like pool noodles. And that is, well, pool noodles. We're a team on a tight budget, so we constantly have to innovate. And this is all part of the day-to-day workings for us. So pool noodles were cut in half using a bandsaw and adhesive down, giving us a structure to lay more fiberglass over. So this method was designed to increase the material height and inherently increase the stiffness of the mold, which is crucial. Once the mold cures, it needs to be pried off the bark. And there are a variety of tools to use, including PDFE wedges and also air-powered blasters. As you pull the mold off, you're able to see if there's any sticking thanks to that red or any bright colored pigment used with the gel coat. It's critical to inspect and repair any surface imperfections. Any slight swirls, cracks, scratches, or chips due to voids will perfectly transfer onto the composite part you create from it. And once you've inspected or repaired any imperfections, the surface then needs to be sealed and a release agent needs to be applied. So what we use are two Loctite branded products to do this. We use B15 and 710NC. So B15 helps seal the surface and acts as a bonding agent for the 710NC. 2 layers of B15 are lightly applied using a lint-free cloth, half an hour between each application. Then the 710NC is applied 6 to 8 times, only waiting for the product to flash off between layers. And after this process is complete, you're ready to move into the next phase. And now that I've talked you through the tooling, mold design, and preparation before use, I'd just like to talk a bit about the composites we use to create our components. So carbon fiber is an incredible material, and it's highly regarded for its lightweight, high strength, and chemical inertness. There are many different types of carbon fiber materials and manufacturing methods, but we mainly use 2 types: pre-preg bidirectional and pre-preg unidirectional. So pre-preg just means the carbon fibers are pre-impregnated with the optimal amount of epoxy. This ensures that the fibers are at peak strength whilst remaining as light as possible. And there's a range of core materials we use in conjunction with these pre-preg carbon fibers, such as honeycomb Nomex, which is essentially Kevlar paper, and foam cores. So think of a sandwich where you ideally have 2 symmetrical pieces of bread on the outside, with the core materials acting as the filling. The pre-preg carbon fibers are stored in a freezer and thawed before use to prevent the epoxy from slowly curing. And once thawed, applying the carbon is very similar to contacting a book. You have to ensure there are no contaminants or air bubbles. We have control measures in place and use methods such as compaction while we work through the layers to ensure the highest quality and safest possible component is created. Now, the fiber direction, type, and even the amount of carbon, as well as what core materials we use where, is all determined through our team of engineers through finite element analysis and communicated through what's called a layup schedule. And hopefully some of you were at Divium's previous session, and you would have learned a bit about that computational simulation side of things. So anyway, once the layup schedule has been complete, it's time to bag the part. And the term bagging is jargon, and it really just describes the process in which the composite part is sealed and placed under a vacuum to cure, ensuring good layer adhesion and tolerance. So all vacuum bags are handmade to suit the application. And imagine wrapping a napkin around a sandwich before cling wrapping it. The component gets wrapped in some specialized materials, sometimes including peel ply and breather cloth to distribute the vacuum evenly and ensure ease of deconstructing after curing. Then a vacuum port is strategically placed and it gets sealed inside a plastic material, except instead of scrunching it shut, it gets sealed around the edges with tacky tape, which is a blue tack-like substance. An incision is made near the vacuum port and the vacuum line is fed in. So whilst under vacuum, our pre-preg composite parts need to be cured inside an oven at temperatures ranging from 80 to 120 degrees Celsius, depending on the type of epoxy system that we're using. And an important thing to remember is ramp up and ramp down times. So that essentially refers to how quickly the temperature increases or decreases to ambient. So for our type of pre-preg and the epoxy system within, it's usually around 1 to 2 degrees Celsius per minute, both for ramp up and ramp down. So if you haven't already noticed, the last vehicle we created, Unlimited 3.0, is pretty long. It's just under 5 meters, in fact. And that really set us with a challenge as the entire shell was cured in one piece, and ovens generally don't come that big to consumers. So we had to innovate, and we ended up purchasing a shipping container and converting that into an oven that was up to the task. So now that you have a part that has been properly optimized and manufactured, you of course need to put it to work. And before you do, there's a few things to consider. In the case of our aero body, we had to color it Western Sydney red. And there were definitely a few options we could have gone with, including vinyl wrapping. However, we ran multiple tests with PPG, who's one of our partners, to determine which method would be the lightest and best for aerodynamics. So we ended up creating our own mixture of lightweight filler to fix surface porosity issues and use as a primer before painting. When painting, we use stencils to paint on the decals underneath the final layer. Most race cars use stickers, but the slight bump created would produce unwanted aerodynamic drag and genuinely affect our performance. So I hope I've covered the key aspects of composite manufacturing, and I'd like to wrap this up by mentioning that our team operates on a tight budget relative to what it is that we're trying to do. So that means we're constantly coming up with crafty solutions, such as building our own shipping container oven to get things done. What I've run through today isn't necessarily suited to all applications, but it worked well for us. So if you'd like to get in contact with our team or have any general questions or questions in regards to composite manufacturing, please reach out using the details up on screen. Now I'll hand over to Kartik to moderate the Q&A part of this session.
Cool, thanks, Brad. It's great to hear, how we get our composite manufacturing done within our team. We've had some good questions in the chat so far. The first question being, how do you ensure sharp edges or points don't rip the composite vacuum bag?
Yeah, so that's a really great question. And one of the key things for us is to ensure that we don't have any, sharp edges that could potentially wreck the bag. In some instances, it's quite unavoidable. So say, for example, in the case of our aero body, where it's a nice airfoil shape and the tail of it, or the trailing edge, is quite sharp, then, we use excess breather cloth to sort of, package that edge and ensure it doesn't rip through the bag that way. But just in general, especially working with molds made out of fiberglass, what we tend to do is, before we seal it in that vacuum bag, we use a material called peel ply. And it's like a gritty, sort of cottony looking material. And we lay that over the fiberglass before sealing it up and vacuuming it. And what that does is, when we take it out of the bag, we kind of just pull that peel ply off and it leaves that surface nice and smooth. Whereas if you don't do that, sometimes what can happen is you can have fibers coming through and sticking up, which will definitely rip the bag. So then, you need to sort of get there with an Orbi or some sort of sanding device and smoothen it out that way. So that is pretty painstaking. And yeah, we definitely have learned that the peel ply method is far better.
Yeah, that's great to hear. Another really good question. What led to the decision of using the three-step process, of using the buck and then fiberglass and then your carbon fiber? What sort of led to, that decision of manufacturing the aero body?
Yeah, great question. And I think with the budget that we operate within, it was by far the cheapest method. It was something that was within sight of our scope. So essentially, if we didn't use a male mold first to then create, female or negative molds to then lay the composite part up in, what we would have had to do is just, machine that negative surface of the skin out of a material like aluminium. We've found that MDF just isn't really up to the application of, pulling the composite part straight off it. So, aluminium at that scale would be quite expensive. So, that three-step process from the buck to the molds to the final part was, what worked best for us.
Yeah, that's great. And another question that we've got is to do with air bubbles when laying up carbon. Do you get them? And is there a possible way to fix a part if it does have an air bubble?
Yeah, absolutely. So we do have pretty effective quality control measures in place. And I mentioned something in the presentation called compaction. but I didn't really expand on that. So I suppose I'll do it now. But basically, compaction is just, putting that part that you're laying up under a vacuum, in between different stages. So your part will, achieve better layer adhesion, compared to not doing that. I just want to check, can everyone still hear me?
Yep, you're all good.
Yep, okay, excellent. So yeah, compaction is one of the main methods. In regards to, do we get air bubbles? Yes, sometimes we still do, it just happens. And you can repair them sometimes. It really just depends on, how bad they are and where they sit. So say, for example, if we're laying up a chassis, and, we have an air bubble or a void, below where we would mount our suspension components, somewhere really structural and, critical to safety, we would probably just start again and not even attempt to repair it. But, if we do have a void in a part such as the aero body, which isn't necessarily a structural component, it's just for aerodynamics, then, absolutely we would repair it. We'd either cut out a small section and just re-laminate, a composite part onto it through a technique or method called wet lam. Wet lamination is, the extension of that. But yeah, I hope that answers the question.
Yeah, that's great. And of course, throughout the team, safety is obviously our #1 priority, which is, leading on from that. Another question we've got here is for choosing the layout of the carbon fiber for its testing through smaller models. Is there a CAD program that allows us to, sort of choose what type of carbon fiber to use, how much to put, that sort of thing, or is it all, done by estimations and, in your head?
Yeah, definitely. So FEA is, the program that we use. So finite element analysis. We use ANSYS, and what we're able to do is mechanically stress test our composite components before creating them. So in FEA, we've basically, got our design. We can select what material we want that computational simulation to run. So, we'll select composites essentially. We'll come up with a layup schedule. So we'll kind of intuitively guess to start out with what we think would work best. And then, we run it, we get results, and we just keep optimizing and going back and forth that way. So, once we find something that works, we're happy in regards to the weight of it, and all those sorts of things, then we're able to produce a layup schedule, which is basically a document that dictates to whoever's doing that layup, exactly what type of carbon they need to put where, how many layers, if core materials need to be used, what sort of core materials you need to use, if there's any glue films required, and all those sorts of things. So yeah, it's definitely not something that's done on the fly. It is determined well before using FEA.
Yeah, lots to consider when going through that, layup process. Another question we've got here, really good one. How do you combine different carbon parts?
Yep, sorry, it just cut out there for a second on my end.
Yeah, how do you combine different carbon parts was the question.
Yeah, okay. So that's a good question. And we did that a fair bit actually. So I'll use the example of TED 3 again. Now TED 3 was an interesting and pretty unique car because it was consistent of, like a different or a separate chassis and separate aero body that were created at 2 different periods in time and bonded together afterwards. So basically, we didn't use any mechanical methods of fastening. We used a structural adhesive called Sparbond, and it's a Gurit product. So, to answer the question in short, we glue them together. But Sparbond, is a very good adhesive, and the particular one that we use is the same one, that's used in industry to glue wind turbines together, and things like that.
Yeah, that's great. We've just got another question in, a really good one about suspension. The question is, I've seen some previous cars of yours use carbon suspension. Why move to aluminium suspension now for TED 3 that we saw earlier today?
Yeah, so we used to make carbon suspension, not in-house. It was externally sourced. And, we've just never really had the capability to do that in-house. I think one of the biggest things as well is with aluminium suspension or with composite suspension, I should say. Sometimes it's worth the extra mile doing it in composites, and sometimes it's not. So, one example that I'll give, again using TED 3 as a reference, is we had double wishbone suspension at the front and the rear of the vehicle. There was transverse mounted shocks and pull rods connected to bell cranks. So, something like the pull rods, we ended up making out of a composite material. So they were carbon fiber pull rods. And, we went through the trouble of actually laminating the tubes in-house, machining out the aluminium inserts. And then what we had to do was post bond them in using that structural adhesive, spar bond. So we started out with the idea and the philosophy of, if we just do everything in composites, it'll be the lightest it possibly can be. But after, all the glue was factored in, and all that sort of stuff, we realized that, it wasn't actually the most optimal way to do it. And because of the use of the glues and all that sort of stuff, and the fasteners to mechanically lock it in as well, we realized some aluminium suspension parts would have actually been lighter and better. So yeah, it really just depends on the application. The other good thing about, aluminium or metallics is they deflect quite nicely. Their failure modes are different to composites. So composites, tend to shear and just fail in ways you wouldn't want a suspension component to fail in, basically.
Yeah, that's great. Constant theme throughout the presentations has been that the team is, it's a learning experience. That's a lot of what you just said there. We'll finish on a personal question for you. Personally, what's your favorite step in the manufacturing process of carbon fiber?
Yeah, I would probably say removing the carbon part from the molds. Until that point, everything is a process. You're pretty focused on doing and working through that process. So you'll get your big MDF block back. You'll sort of paint it, looks pretty cool, but you're stuck into making sure the surface is nice and smooth. Then you'll do your molds. Sometimes it is quite painstaking. I think for me, the first really rewarding and satisfying moment is seeing that carbon part pop out of those molds. I think once it's come to that point, unless something goes wrong during the layup or during curing, that's when it all becomes real. All you've got left to do, I say all you've got left, it's still a fair bit of work, but all you've got left to do is, either paint and finish it or prep it to bond to something else. So I think that's definitely it.
Awesome. Well, that's great to hear. Thanks so much, Brad, for your awesome insight today from your experiences and what the team does with composite manufacturing. If you do have any other questions or anything like that from any of the technical presentations today, you can find our details on our website, and specifically to LEAP and our other partners as well. But yeah, thanks all for coming. Throughout the rest of the afternoon, we've got a lab tour coming up and a team update, followed by a Q&A session with the broader solar car community. But thanks everyone for coming, and hope to see you later in the afternoon.
Thanks everyone.